Hi guys, Mr. Kennedy here. This is your Chapter 2 lecture notes on basic chemistry for biology at Clovis West. Today we're going to learn a little bit about atoms and molecules, why atoms interact with other atoms. This is supposed to be something that we learned back in junior high, so you could kind of consider this maybe a little refresher. If you remember it from that point, great. If you don't, this is your chance to get it. Okay? So first thing that I'd like to do for you here is just introduce you to the idea of matter. Okay, so what is matter? Not what's matter, but what is matter? Okay, matter, basically, if we define it very simply, is anything that has mass and takes up space. Anything that has mass and takes up space. You might know matter in one of its three forms that you learned in junior high: a liquid, a solid, or a gas. Okay, now if you're super science savvy, you might know that there is a third phase or state of matter that you might learn in chemistry or a physics class called plasma. We don't deal with that in biology, so it's not on this slide. We're just going to pretend like it doesn't exist for now. So matter exists in three forms: solids, liquids, and gases, and its definition: anything that has mass and takes up space. Now before we leave this, I just want to touch on the idea of how matter goes from a solid to a liquid to a gas. Matter is made up of tiny particles that we refer to as atoms or elements. Those atoms are constantly moving, constantly. If we get them to move faster by adding energy, maybe in the form of heat, then we can take something that is solid and move it along the matter spectrum to a liquid or to a gas. If we take energy away, then the opposite is going to happen. Something that is a gas might become a liquid and eventually a solid. Okay, how do we take energy away? Well, put something in a refrigerator. That's going to slow those molecules down. That's going to take heat energy away, and you'll go from a gas to a liquid and maybe eventually to a solid. Okay, so when we think about matter, matter is made up of elements. An element is any substance that cannot be broken down into smaller parts or more simpler substances. A great example of an element are the things that we see on the periodic table. There's a picture of the periodic table in your textbook. According to chemistry, there's 92 naturally occurring elements on this planet and a few that are man-made. Thank goodness you don't have to memorize them all. There will eventually be like 6, maybe 7 that we'll spend a lot of time with in biology. You'll learn those in another lecture on organic chemistry that will follow this one. For now, just think about elements on the periodic table like what I have for you here. The element sodium. When you look at the periodic table and you see the letters Na, that's the element sodium. When you see a K, that's potassium, right? If you see an O, it's oxygen. A C, it's carbon. An H, it's hydrogen, right? You get the idea. Those are our elements. Elements are made up of these guys, atoms. The smallest particle of an element that retains the properties of an element is an atom. And like I said, many of you probably remember studying this in junior high. Okay, if that's the case, fantastic. You're ahead of the curve. If you don't remember this stuff, make sure you're getting it down now, because you're going to need this when we get into organic chemistry. So an atom. If we just keep things simple, we use that KISS principle. Atoms are made up of a few subatomic particles that you need to know for this class. The two big divisions of an atom are the nucleus and the electron cloud, as you see here on this slide. The nucleus is made up of a proton and neutrons. The electron cloud is where we find all of our electrons. Now, outside of that, there's some other particles that you need to be familiar with. Inside the nucleus, I said, are protons and neutrons, and you can see here protons and neutrons are more than just particles inside the nucleus. Protons carry a positive charge as they live inside the nucleus. Neutrons, they don't have a charge. So in a sense, they are neutrally charged. Okay, there is no charge to a neutron. Now, if you have something that is positively charged and something that doesn't have a charge together in the nucleus, what's the charge on the nucleus as a whole? Well, it's positively charged, because the only thing that's carrying a charge in there, protons, is positively charged. Outside of the nucleus is the electron cloud. And guess what lives in the electron cloud? You guessed it, electrons. Okay? So these electrons, they're all negatively charged particles. They orbit the nucleus because opposites attract. The positive nucleus attracts the negative electrons. Usually, those two entities balance each other out. So let's say if you have 5 protons in the nucleus, you'll have 5 electrons in the electron cloud to cancel out that charge. That's the normal circumstance for an atom at what is called its ground state. Not all atoms stay that way their entire quote-unquote life, but that's normal for what you see on the periodic table. Okay? That brings us to compounds. So, a moment ago I said that positive charge and negative charge on atoms should balance themselves out for an atom at ground state. And I also said that's not always true for all atoms. Compounds form in that latter example. When atoms get to a point or they find themselves in a situation where their charge is unbalanced between the nucleus and the electron cloud, to give it a human term, they're going to do something about it, right? Now, what they do about it is they find another atom to interact with so that they can balance that charge and become overall neutral, okay? Atoms, kind of like people, have quote-unquote goals for their life, right? Maybe Mr. Kennedy's goal is to make $1 million before I retire. You might have different goals. I don't know. But for an atom, there are these things that we put under the umbrella of the word, the octet rule, O-C-T-E-T rule, octet rule. The octet rule basically gives us the life goals for an atom. One of those life goals says that all atoms want their outermost energy shell to be full. So what does that mean? Well, if an atom only has one energy shell around the nucleus of the atom, that outer shell can hold a maximum of 2 electrons. That atom will only be happy if its outer shell has 2 electrons in it. If it doesn't have 2 electrons in it, that atom's going to find another atom to interact with so that it can get 2 electrons in its outer shell. Okay? One way that we can illustrate that, if you look closely at the picture right underneath me, is the atom hydrogen. Okay? So I'm going to try to make this a little bit bigger for you here, right? So that you can see what I'm drawing. So there's the atom hydrogen with an H. Hydrogen has 1 proton and it has 1 electron. Okay, 1 proton, 1 electron. Now, if we drew this in a molecular formula, that would mean the nucleus would have a proton like this, and the outer shell would have 1 electron like that. Okay? Now, I just told you a moment ago that atoms are only going to be happy if their outer shell is full. This atom only has 1 electron shell, and in that electron shell, there's only 1 electron. Atoms in this condition are only going to be happy if their outer shell actually has 2 electrons. So my question for you is hydrogen happy? Is hydrogen happy? You should be saying no. Okay? Hydrogen is going to seek out other atoms to try to add an electron. This is going to create other problems for hydrogen. We'll deal with that as it comes, but that's rule number 1 in the octet rule. Atoms want their outer shell full. If you have more than 1 shell, this would mean we would have to change atoms. Each shell after the first one, this is the first shell, second shell, right? Out here to the third shell, and so on. Each of these can hold 8 electrons. So the atom will work really hard to get 8 electrons in each of those outer shells. And it won't be satisfied or happy until it does that. Okay, so filling the outer shell is super important to the atom in making sure that it is quote unquote happy. Okay, the second thing that it wants in order to be happy is it wants all of these electrons in these outer shells to have a partner, paired up, 2 electrons, okay, paired up. So that kind of means that each of these shells has to have an even number of electrons in it. If there's not an even number of electrons, again, the atom will not be happy, and it's going to work hard in order to accomplish that. The last thing, right, that we need to take into consideration, I'll repeat those rules again. We got to have our outer shell full. We got to have our electrons paired up. The last thing is the atom wants to have an overall neutral charge. It doesn't want to be +1, +2, +3, have an unequal charge, right? Anything like that. So these energetic tendencies, as we call them in chemistry, drive the formation of compounds. Okay, so let me get this out of the way. Move this right back up here for you. Okay, and then we'll go back to talking about compounds here. Okay, so when you think about a compound, right, a compound is a substance that is made from chemically combined elements. Why do they chemically combine? Because like I said, atoms want to be happy. And to be happy, you have to meet all of those criteria I just mentioned. Outer shell full, electrons paired up, right? To be energetically neutral. And if you're not those things, okay, then your atom is not going to be happy. Okay, so let's move on and look at the next piece here, molecules. When 2 or more atoms interact with one another, not only do they form something called a compound, but they can form a thing called a molecule. By definition, a molecule is the smallest unit of a compound that still has all the properties of that compound. Sorry for the little typo there on water, but take water as an example. If you think about water as a liquid filling a cup, right? It's a compound because you've got 2 hydrogens bound to 1 oxygen, right? 2 different atoms bound together in order to be stable or happy, and that is the definition of a compound, right? It's also the definition of a molecule. H2O is a molecule. H2O is also a compound because we have 2 or more different atoms bound together. One thing I do want you to know about the relationship between atoms and molecules is all compounds are made up of molecules, but all molecules are not compounds. Okay? You need to have 2 different atoms, well, 2 or more different atoms bound together to make a compound. To make a molecule, you just need 2 atoms. So if I have H2 as a chemical formula, that's just 2 hydrogens bound together, or O2, which is air, okay? That's not a compound, but it is a molecule because we've got 2 atoms bound together. All right, moving right along. Okay, changes in matter. So when atoms interact with other atoms and they form these compounds or molecules, we get changes in matter, right? Now, I'm not just talking about going from a solid to a liquid to a gas here. I'm talking about like hydrogen, which is a gas, and oxygen, which is a gas, combining to make water, H2O. Now, that water they form could still be kind of in the form of a gas, could be water vapor, could be liquid water, could be frozen water or solid. But the point is, hydrogen and oxygen have come together, right, to form something totally different. Water from 2 gases, okay? Why did they do that? Remember what we just talked about, okay? They did that because maybe oxygen wasn't happy in its original state, its outer shell wasn't full, its electrons weren't paired up, it wasn't electrically neutral, like that's why it did that. Same thing for hydrogen. Now, when atoms interact with other atoms, they form bonds. It's kind of like friendships or relationships, right, that these guys can form with one another. One type of bond is a covalent bond. Covalent bonds occur when atoms actually share electrons with one another. That sharing of electrons kind of like the glue that holds them together. It's pretty cool. Okay, so carbon and oxygen will actually come together to try to satisfy each other's needs based on what we've learned already. Maybe there weren't enough electrons in the outer shell. Maybe it was electrically neutral, right? Stuff like that. And as they share electrons, that's the glue that holds them together. Okay. So you could think about two people like, I don't know, sharing a jacket. Okay, like you have your favorite jacket and you loaned it to your best friend. Okay, you guys are going to share that jacket back and forth. That creates a bond between you as you share that garment. Another type of bond is an ionic bond. Ionic bonds occur when two atoms exchange electrons. So again, why did they do that? Well, maybe there weren't enough electrons in the outer shell. Maybe it wasn't electrically neutral. Maybe the electrons weren't all paired up. At the end of the day, the atoms interacted with other atoms to try to balance all that out. The one example that I always see in kind of like every science book that ever talks about ionic bonding is table salt. Sodium interacts with chlorine to balance out all of those things that I gave you a while ago called the octet rule, right? In its ground state, sodium's not happy because its outer shell's not full. Its ground state, chlorine's not happy because its outer shell's not full. Well, to fill the outer shell, in the case of each of these, there needs to be an exchange of an electron. So they swap electrons. Their outer shells are now full after the swap. The problem is now they're charged. Well, what do I do about that? No problem. I just hang out with the guy I got the electron from. That balances out my charge and everything's hunky-dory. See the picture in your textbook, okay? It'll explain and show you what I mean. All right, moving on from there. There is a type of bond called a polar covalent bond, a third type that I want you to be familiar with. This occurs when atoms share electrons, but they don't really share equally, okay? It's kind of like your buddy saying, hey, here's a candy bar, let's split it. But instead of splitting it right down the middle, right, your buddy only gives you like this little bitty piece off of the end. And you're like, bro, where's the rest of the candy bar you said you were going to share with me, okay? So polar covalent bonds, yeah, there's sharing that goes on for the same reasons we've already talked about. Outer shell not full, electrons paired up, all that stuff. But the problem is the electrons aren't shared equally. So they spend way more time with one of the atoms in the relationship than they do with the other, as opposed to sharing in both places equal time. Okay. Last bond I want to give you is a hydrogen bond. This is just kind of like static clinging between atoms. They're weak kind of electrostatic attractions, right? So if you imagine when you get your laundry out of the dryer and you hear all that popping going on, it's that kind of thing. Hydrogen bonds are very weak electrostatic attractions. The bonds are easily made and easily broken. All right, we're almost done. So to make these bonds, what we're doing is a thing called a chemical reaction. Chemical reactions are basically the process by which atoms react to form new compounds. And I've really kind of already explained how this happens with the whole exchanging of electrons thing. So we don't have to spend a lot of time on it, but there are some parts of a chemical reaction that you do need to know. So when you think about chemical reactions, you definitely have to know the difference between a product and a reactant, okay? Products and reactants. Reactants always start the reaction. Products always finish the reaction. That's what the reaction makes. So if you look at this little guy right here, okay, CO2 plus H2O, and then you got this arrow thing. In chemistry, we read the arrow as the word yields. And then we got this big old thing, C6H12O6 plus O2. All right. So the reactants are always over here on the left, and the products are always over here on the right, okay? And then this arrow in the middle, it usually only points one way, from left to right. That's normal. This arrow is pointing both directions because this is what's called a reversible reaction, so it can go either direction, right? So if that confuses you, I'm sorry, but normally we go from left to right, reactants, and then the arrow yields, and then products. So if we say it all together, it's CO2 plus H2O yields C6H12O6 plus O2. If we just use plain English, it's carbon dioxide plus water yields glucose and oxygen. Why did these atoms react? Because they weren't happy in their ground state. Their outer shells weren't full. They weren't electrically neutral. Their electrons were not paired up. So they sought out other atoms and other molecules in order to reach that stability, their life goals. Now, last thing that we got to mention here is the eventuality where atoms, molecules, compounds, they interact with other atoms, molecules, and compounds, but they maybe don't necessarily chemically combine. That's mixtures and solutions. When you're chemically combined, you've actually formed a bond. If you're not chemically combined, you're just like hanging out, okay? So if we took the football team and, I don't know, we had like a school dance and we invited all the football team and the volleyball team and the cheerleaders together, well, each of those teams could be like an element, and as they mingle on the dance floor, they form a mixture of students. They're not chemically combined. We could easily pluck a football player out of the gym. We could pluck a cheerleader out of the gym, a volleyball player out of the gym. That makes it a mixture, okay? If we turned on the fire sprinklers while they were all in there and got everybody wet, now you'd have a solution. When you put a mixture in water, you make a solution. Obviously, everybody in the gym would not be real happy with Mr. Kennedy, but that's how it happens. So a mixture occurs when any two substances cannot be chemically combined. If you take something like oil and water and you mix them in a container, a glass, a water bottle, and you shake it up like you're making salad dressing, that's a mixture. Mixtures will tend to settle or separate over time into individual layers. Salad dressing, okay? If it's a solution, then that mixture has a liquid component to it. So if you take, again, salad dressing, and now you're going to put in all the little spices to make it like Italian salad dressing, well, now you have a solution. So all those little spices that are floating around in your Italian salad dressing, that makes your mixture a solution, okay? All right, so I hope you've enjoyed this lecture on Basic Chemistry, Chapter 2 for Biology. I'll see you next time.